Plate tectonics is a fundamental geological theory that explains the large-scale movement of the Earth's lithosphere. This concept has revolutionized Earth sciences by providing a coherent explanation for various geological phenomena, such as the formation of mountains, earthquakes, and volcanic activity. The theory evolved from Earth concepts like continental drift and sea floor spreading, and now the accepted explanation for the dynamic nature of Earth's surface. This essay will explore the origins of plate tectonics, the structure of the Earth, the mechanics of plate movements, the different types of plate boundaries, and the resulting geological phenomena.
Right here? Origins of the plate tectonics theory. The plate tectonic theory has its roots in the early 20th century, primarily due to the work of Alfred Wegener. In 1912, Wagner proposed the theory of continental drift, suggesting that the continents were once a part of a supercontinent called Pangaea. How do you say that? Pangaea, I'm sorry, and have since drifted apart. He pointed to the jigsaw-like fit of continents, notably South America and Africa, and the similarities in the fossil record across continents as evidence. However, Wagner's theory lacked of plausible mechanism to explain how the continents move, leading to the skepticism. It wasn't until the 1950s and 1960s with the discovery of seafloor spreading by Harry Hess and the understanding of Earth's magnetic field reversals, and scientists began to accept the idea of moving plates. The final breakthrough came with the realization that the Earth's outer layer, or lithosphere, is broken into plates that move over the semi-fluid atmosphere, driven by forces originating in the Earth's mantle. Structures of the Earth. The Earth is composed of several layers. Core, at the center of the core, divided into a solid inner core and a liquid outer core, primarily made of iron and nickel. The movement of molten iron in the outer core generates the Earth's magnetic field. Mantle. Above the core is the mantle, a thick layer of silicate rock that extends up to the Earth's surface. Although the mantle is solid, it behaves plastically over long timescales, allowing the slow movement of material. This connective motion drives the movement of tectonic plates.
Lithosphere and asthenosphere, the Earth's outermost layer is the lithosphere. Composed of the crust and the outermost part of the mantle, it is rigid and brittle, broken into tectonic plates. Beneath the lithosphere is the asthenosphere, a ductile region of the upper mantle that can float over time. This allows the rigid plates to move over it. Types of plates and their movement. The Earth's lithosphere is divided into several tectonic plates, which can be classified as major and minor plates. Major plates include the Pacific Plate, North American Plate, Eurasian Plate, African Plate, South American Plate, Antarctica Plate, and Indo-Australian Plate. Minor plates include the Nazca Plate, the Philippine Sea Plate, and others. The movement of these plates is driven by several mechanisms. Mantle convection. Heat from the Earth's core causes the mantle to convect, with hot material rising and cool material sinking. These convective currents in the mantle drag the overlying plates along. Ridge push. At mid-ocean ridges where new oceanic crust is formed, the lithosphere is elevated. Gravity causes the plates to slide away from the ridge, pushing them apart. Slap pull. At subduction zones where one plate is forced beneath another, the weight of the sinking plate pulls the rest of the plate with it. This is one of the strongest forces driving plate movement. Types of plate boundaries. The interactions between tectonic plates secure their boundaries, which should be classified into three main types. Divergent boundaries. At divergent boundaries, plates move away from each other. These boundaries are commonly found along mid-ocean ridges where new oceanic crust is created as magma rises from below the Earth's surface. This process, known as seafloor spreading, continues to add new material to the plates. A well-known example is the Mid-Atlantic Ridge. On land, divergent boundaries and form rift valleys, such as the East African Rift. Convergent boundaries. At convergent boundaries, plates move towards each other depending on the types of plates involved. Different geologic features are created. Oceanic continental convergence. The denser oceanic plate is forced beneath the lighter continental plate, forming deep oceanic trenches and volcanic mountain ranges such as the Andes. Continental convergence. When two continental plates collide, neither plate is subducted easily. Instead, the collision causes the crust to buckle and form mountain ranges such as the Himalayas. Transform boundaries. At transform boundaries, plates slide past each other horizontally. The friction between the plates prevent smooth motion, leading to the buildup of stress that is released as earthquakes. A famous example of a transformed boundary is the San Andreas Fault in California. Consequences of plate tectonics. The movement of tectonic plates is responsible for many of the Earth's most dramatic geological features and events. Earthquakes. Most earthquakes occur along plate boundaries where the stress of moving plates is released in sudden bursts. Transform boundaries where plates slide past each other are particularly prone to earthquakes. The San Andreas Fault is notorious for its seismic activity. Mountain building. The collision of plates at convergent boundaries, especially continental collisions, leads to the formation of mountain ranges. The ongoing collision between the Indian and Eurasian plates, for instance, continues to raise the Himalayan mountains. Continental drift. Over millions of years, the movement of tectonic plates has caused continents to drift across the Earth's surface. This explains why continents like South America and Africa now lie far apart but share geological and fossil evidence of their former proximity. Ocean basin formation and destruction. Divergent boundaries at mid-ocean ridges create new oceanic crusts, expanding ocean basins. At the same time, subduction at convergent boundaries destroys older oceanic crusts. This process leads to the opening and closing of ocean basins over millions of years, as seen in the cyclical assembly and breakup of supercontinents like Pangea. Future of plate tectonics. Plate tectonics is an ongoing process, and the Earth's surface will continue to change in the future. Scientists predict that over the next 250 million years, the continents may converge again to form a new supercontinent, sometimes referred to as Pangea Proxima. This continuous cycle of supercontinent formation and breakup has occurred several times in Earth's history. Conclusion.
Conclusion. Plate tectonics is a powerful theory that explains much of the Earth's geological activity and structure, from the formation of mountains to the occurrence of earthquakes and the drift of continents. Plate tectonics provides a framework for understanding the dynamic nature of our planet. Ongoing research continues to refine our understanding of the forces driving. Understanding the forces driving plate movements and their impacts on the Earth's surface, shaping both the landscape and the life that inhabits it.